This meeting is being recorded.
I'm not sure I understood the question. Always considering the derivative is complete, there are no assumptions being made.
I remember one of the last 2-3 slides you said that the assumption we're making is that the neurons in the same layer are not affecting each other.
That's because the activations are local, right?
Right.
If you have a vector activation like in the softmax, you cannot make that assumption.
Right. Got it.
Yeah?
Yeah.
So,
Professor, how can we know which TA mentor is being assigned to our group?
so is that assignment not yet been made public? It should have been made public.
All right, I'll check Piazza. Right.
Okay, and if it is not, then let me know. And this information was supposed to have gone out last weekend. We are behind. Right? It's there. Not only do you have the information, I want all of you guys to reach out to your mentors and reach out to your study groups. Tomorrow is a good day. Get together, sit down for a couple of hours together and work out homework 1P2. Now,
would the TA mentor be able to help with implementation, or he's only gonna help with concepts?
well, we want you guys to implement as far as possible, but if you're stuck, they will help. Right?
Oh,
So,
okay.
I mean,
so if we are stuck, he or she will be able to give out hints.
yes, or more, because we want to get you across the line, right?
All right, thank
So
you.
I strongly recommend that you get together and do a homework hackathon tomorrow. And I assure you that if you do it right, you should at least get to the 70.78% accuracy performance. Anyway, let me begin. So here's the story so far. We've seen that neural networks are universal approximators. They can model any odd function, provided they have the right architecture. But then you must train them to approximate any function, meaning you specify the architecture and learn their weights and biases. And the way you train them is to minimize the total loss on a training set, which we do through empirical risk minimization. And we use variants of gradient descent for this purpose. Now, the gradient of the error with respect to network parameters is computed through backpropagation. So here is the general framework we had. We had a collection of training instances. You define the loss as the average divergence over all of the training instances. Training happens in a two-step process. First, you compute the derivative of this loss with respect to all the network parameters. And the derivative of the loss with respect to any network parameter is the average of the derivative of the divergence for the individual training instances with respect to that parameter. So once you compute this guy, then you can plug it into backpropagation, into gradient descent. And this highlighted term, which is the derivative of the divergence between the actual and desired output of the network for a single training instance, that is computed using backprop. So wait, here was the pseudocode, slightly compressed. It has two parts. The outermost loop is where you go over many iterations until your loss is converged. Within that, you have two blocks. The first block goes over all of the training instances. For each training instance, you compute the derivative of the divergence for that training instance with respect to network parameters and then accumulate them. So this portion computes the gradient of the loss with respect to network parameters, one instance at a time. So this individual instance gradients is computed using backprop. The second block now uses that gradient to perform gradient descent. So backpropagation is not gradient descent. Backpropagation is not training the model. Backpropagation is doing one and only one thing. It is used to compute the derivatives of the loss for a single training instance with respect to network parameters, right? So then we have our first poll, which I call poll 0, because you will be able to answer this poll only if you have seen these slides or the part 2 of Tuesday's lecture. So 10 seconds, guys. All right, let me stop this. So the first one is right. We had had explained this in, there's my whiteboard. For some reason, my whiteboard has disappeared. Okay, so the way we had explained it in class, when I'm using the column vector notation, for any layer, if I have yk minus 1, this is the vector of outputs of the previous layer. And then you have the wk, and then you have the affine value at the kth layer. And from these, you compute the divergence. Then the derivative of the divergence with respect to wk was this vector, yk minus 1, times the derivative of the divergence with respect to zk, which is the derivative of the divergence with respect to zk. And you can see that this will be a vector. This will be a matrix. If you have m neurons over here and n neurons over here, this is going to be a m cross 1 vector. This is going to be, because this is a column vector of size n, its gradient is going to be a 1 cross n row vector. And the product of the two will be an m cross n matrix, which is the same shape as the transpose of W. So again, this is just to remind you how that worked. TU, where is that? Out here. That was the number of training instances. Remember, the loss is the average divergence over the entire training data, right? We said we were going to minimize the error over the entire training set. Now, so let's get on with the topic. Any questions, guys? Any questions? Okay. So now let's get on with the topic of today's lecture. We're going to, these last two topics will be in tomorrow's and next week's lecture. Today, we're going to look at whether backpropagation always works, and when it does, what are the restrictions, right? So first, here is my question. I'm calling this backprop, but basically I'm speaking of gradient descent where the derivatives are computed using backprop, okay? So suppose you define a loss function, which is the average divergence between the average of the divergences for the entire training set. And then you can try to minimize this loss function using gradient descent. Now let's say that you actually manage to find the minimum in this of this loss function, the parameters that minimize this loss function. Will those parameters actually give you the actual answer you want? Now, going back to the couple of classes, what was the actual objective we wanted to minimize for a classification network? Yeah, I mean, global minimum. Let's say you find the global minimum, right? So what is the actual objective you're trying to minimize? Was it the expected divergence or was it the expected error, right? The true error is what you wanted to minimize. You wanted zero classification error. Will minimizing the divergence actually minimize the error? Not necessarily. Let's see why, right? Remember, this was the objective function we actually wanted to minimize, right? But what we actually did was to have a softer version of this classifier. And instead of just saying, is it right or wrong? We were sort of trying to compute a distance, how right or wrong it was. And this was what we were trying to minimize. But this has a consequence, right? Now, if I increase, because of the nature of this function, every single training instance has some distance to this line. It may be very small, but it always has some distance to this line. So if I have a very large number of blue points right here, then because these blue points want to minimize the error to the line, they will push the curve out right so that every one of them falls on an increasingly flat portion of the line, and thereby actually force the training to cause an error on this instance. To see how that works, let's look at a visual example. The idea is the classification error is non-differentiable. The divergence function minimized is only a proxy, and minimizing the divergence may not minimize the classification error. So here is a very nice paper by Brady, Raghavan, and Sloney in 1889. Let's say I'm going to compare two models, right? The first model is a regular perceptron, which has a, why is this not clear? So the first one is a regular perceptron, which has a threshold activation. And I'm going to be using the perceptron rule, which we learned about, right? In the other one, I'm using a logistic function over here. And these are the two models I'm using, right? Now we are saying that the divergence is a proxy for the classification error, right? So I'm going to be comparing these two models. Then here, in this example, the red data belong to one class, the blue data belong to the other class. Now, does everyone agree that both of these models are capable of classifying this data? Okay. Now, suppose I learn a classifier using the perceptron classification rule. Will it find the classifier?
Yes.
Right? And what about if I minimize the KL divergence for the softer version of the model? Will that find the classifier? It should, right? But now I am going to add a red dot out here where my arrow is, okay? If I add a red dot out here, are the classes linearly separable? Still yes.
Separable.
Will the perceptron find it?
Of course. Of course.
That's right. It will find it. So let's say I add a dot over here. The perceptron rule will find it, right? What about the softer version with the logistic function and where I'm using the average divergence? Will that find it? Because what happens is this one instance is contributing so little to the overall loss that the change in the result is going to be fairly minimal, right? Does it make sense? Right. So, because if I have millions of these red and blue guys and I add one more dot, the total loss contribution by these millions of guys is so large that this red dot is going to be insignificant. All that will happen is that the solution will change a teeny weeny bit. Now, if I
Professor,
yeah,
are we saying the model will never find it?
we are saying that the global minimum of the loss function is going to be that red line.
Okay.
Correct? The model is capable, but your proxy loss, the minimum of the loss function is not the solution you want.
All right. Thank you.
Correct? Similarly, if I change this, if you continue training only on the outliers, yeah, because then you're removing the bulk, right? Now, suppose I change that one spoiler to this point, then what happens? So again, Oscar, each one of these guys is contributing something to the loss, correct?
Yes.
If I have like an infinity of these, every one of them is trying, and an infinity of these, every one of them is trying to give you a loss function which has a solution on the dotted line, right?
Right. Yeah.
If I add this one dot, how much is that considering that I'm taking the average divergence as my loss function? How much will that loss function change?
All right. Yeah. Okay. Yeah. I think I get it.
Correct? So
Yeah.
now, if I change the one spoiler to this guy, the perceptron rule will still find it. What happens to our gradient descent solution, that's going to perturb the solution a little bit.
Yeah.
I change that one spoiler to this point, the perceptron rule will now find this decision boundary. What about the
Alright.
gradient descent rule? It's still going to find this guy, right?
Yeah.
This
But you
is
do
just-
gain stability.
Pardon me?
But you do gain more stability with the
Thank you, right? So these spoilers, the perceptron may change greatly upon adding just a single new training instance because it fits the training data well. So the perceptron rule has, this word should be because the perceptron rule has low bias. It's going to get the classifier every time, right? But what is the consequence? I can change my answer wildly by just moving 1 point, right? So no, Debayan, it's a divergence. So what happens over here? Does this softmax ever, this logistic ever become exactly 1 or exactly 0? Debayan? Right, so that's why, right? And as a result, what you get is that the perceptron rule has low bias. It always gets the correct answer, but it can be made to move wildly by just changing 1 point. Whereas the proxy that we use, the loss-based solution, prefers consistency over perfection. So the variance is low at the potential cost of bias. Which of these two would you choose?
It's a
If you had to
balance.
check. So of these, in this case, which of these two things do you think is the better behavior? You really you don't want to be completely destroyed by a single outlier, right? Or a small number of outliers. So in general, we prefer the low variance solution because you assume that is because consistency is good. Now that's not just for single perceptrons. This also happens if you have a more complex model. A more complex model is going to get a decision boundary of this kind for these data. But then if I add one more training instance out here, which is a spoiler, it's not going to swing around and make this your decision boundary. It will maybe just perturb it a little bit. So in general, what we find is, I'm using the term backpropagation over here because that's what is used in the original paper. It will often not finding a separating solution, even though the solution is within the class of functions learnable by the network. Because as you will see over here, both of these solutions can be represented by this model. It just so happens that our loss function doesn't find it. The minimum of our loss function doesn't find it. So the separating solution is not a feasible optimum for the loss function. One resultant benefit is that backprop trained neural network classifiers have lower variance than an optimal classifier for the training data, because it's optimal for the training data, but it may not generalize. Right. So Anil, it doesn't matter how many times you train it. The point is that I'm speaking of the global minimum of the loss function, right? The global minimum of the loss function is not not a classifier that will actually separate the data. That makes sense? Neil? Okay, he's not replying. Anyways, does this mean backprop is resilient to overfitting? All we are saying is that in general,
Professor,
yeah.
sorry, a quick question. So if we use the logistic regressions for the case you show us, and use the backpropagations, do you mean that it is possible for the model to learn both of these two boundaries, and which cause the backpropagation fails? I just didn't catch the key point of why you say the backpropagation fails.
I'm saying that over here back gradient descent, the global minimum of your loss function is going to be the red line.
Yeah.
Even though the model is capable of representing the dotted line.
Yes, but if we get this local global minimum, and it's still the only global minimum, and is explainable for this case, right?
Speaking of global minimum, so yes.
I see.
right?
Thank you. Yeah. Got it.
Right. So, because Hussam, you don't want the model to just swing around because you added one nasty training instance. You'd want it to be resilient to outliers. Yes, there's an implicit form of regularization. Okay. So now here's a loss. So here's a point. This is an easy one. 10 seconds, guys. I'm very sorry. This.
Professor, is this related to regularization?
This is not, yes, it is related to regularization. You are in fact correct. And I will explain, we will get to that when regularization comes up. If any of you remember the slide, I would like you to remind me, right? So this is clearly false. Now let's go back to our problem. Now, I've assumed so far that the loss objective has a single global optimum, and that could be found, right, in the explanation, but then things get much worse. As you all rightly point out, the loss function is complex. You can have many local optima. So Alex, the point is, if the linearly separable samples you saw might be just an artifact of your specific training instance, training data. So for example, if I go back all over here, if you took a large enough sample of training data, you may actually find that the blues go over here and the red goes over here. But if you make this training data small enough, eventually you'll get separable training instances, but they are not representative. Right. So what exactly does this loss surface look like? The popular hypothesis is that in large networks, loss surfaces have many more saddle points. Saddle points are points where the function is curved in one way along one direction and in a different way along another direction. And the hypothesis is that you have many more of these than actual local minima. And for very large networks, there's some proofs which say that the loss function will have lots of local minima, but all of them are roughly equivalent in the sense that the loss value at these local minima are not going to be very different. For small networks, this is not necessarily the case. So again, what do I mean by a saddle point? It's some variant of a structure like the one at the bottom. And what happens is that right at this point, the derivative in every direction is 0 because it's derivative both along the upward curving direction. It's 0 both along the upward curving direction and along the lower downward curving direction. But you definitely don't want your algorithm to get stuck there. So basically, we are not going to be discussing that. We'll look at that. That's a little too deep for this lecture, but yes, we can take that offline. Let me continue with what we've got. We'll talk about Hessians, right? So you cannot use Hessians to avoid saddle points easily. Let's see. Let's find out whether this is even a problem, right? The loss function may have a large number of unpleasant saddle points or local minima, and backpropagation may find it. So the question we want is, does backpropagation always converge? How long will it take? And MLPs are really complex machines. So I'm going to look at it through the lens of convex optimization. The reason for this is that you must have heard of this famous streetlight effect. This guy lost his keys in the bar, and the policeman found him searching for them under the streetlight because it's dark in the bar. You might as well look where you can see. It's an old joke. And so for us, this is our convex optimization point. But if you understand what's going on here, maybe you can get a better picture of what's happening elsewhere. So what do we mean by convex? How many of you know what a convex function is? at least a few, right? So how do you define it? Can anyone tell me?
If you take any 2 points on a convex function, the value of the function lies between below the line that you form by joining those.
So I plotted it up here, right? If I have a function of this kind, if I take any 2 points on the function, and if I draw a line between the two, then if all the all the points in the function are going to lie below the line, like here. So this is a convex function. On the other hand, this one below is not a convex function, because if you look at this black line, there are portions of the curve between these two endpoints which actually lie above it, right? So it's kind of, you can think of it roughly as bowl shape. You can also define convex sets. A convex set is a set where if you draw a line between any 2 points within the set, all points on the line are also within the set. So this is a convex set. This is a not convex set. I don't know why it's called convex and not concave. That's the standard terminology. So what do we mean by convergence? An iterative algorithm is said to converge to a solution if the value updates arrive at a fixed point, right? So if this is my loss function, I'm showing you the contour plot of the loss function. So every curve is a level set. On every continuous curve, the value of the function is the same. So if I were to use gradient descent to try to find the minimum, if my gradient descent solution sort of monotonically comes to the solution over here, then it's converging, because eventually it's going to get here. On the other hand, your gradient descent solution can also end up doing something like this. Instead of arriving here, it gets close and begins bouncing around. So this would be a jittering solution, or you can have something worse happening. Instead of sort of coming to the solution, it can keep getting farther and farther away. This is a divergent solution. This top kind of behavior is the one we want, because you want to find that solution, right? So let's try to look at it from the perspective of convex functions, specifically quadratic functions. Quadratic functions, it turns out, are really nice to analyze. In some sense, they are the best kind of convex function. So let's say I have a quadratic function of this kind. Some E equals half AW squared plus BW plus C. This half is for convenience, okay? Now, if I give you a quadratic function of this kind, do you know how to find the minimum of a quadratic function? You've all done this in school, right? How do you find the minimum of a quadratic function?
Use the formula.
Take the derivative, set it to
Differentiated.
yeah, okay. But you can also solve this, and there's a form, minus b plus or minus square root of b square minus 4ac over 2a. Remember? So, now here you can also do this using gradient descent. I can start off with an initial guess w0, and then I can keep using this gradient descent formula, right? Now, if I'm using gradient descent instead of just solving directly for it, then is there a step size that will get me from my current estimate to the minimum in one step? Is there a
Yes.
step size? What is that step size? Okay, so let me solve this for you. How many of you are familiar with the Taylor expansions? What is a Taylor expansion? Can you tell me?
It's an approximation of the derivative.
Taylor expansion says that if you have a function that is
yeah.
differentiable everywhere, then you can say f of x is going to be f of x0 at any x0 plus, what was it? F prime of x0
Times the
x minus
times,
x0
yeah. So times the distance, and then f prime,
plus
like the second derivative.
half double prime of x0 x minus x0 whole square, right? Plus 1/6 f triple prime of x0, the third derivative, x minus x0 whole cubed, and you can keep going, right? So this is your Taylor series Taylor series expansion. If you take the infinite expansion, then it's going to be completely accurate, right? So in the case of a quadratic, how many terms will this have?
2?
Only
Uh,
2.
3?
Because
Yeah,
only the first 3, because these you don't have the third derivative onwards, right? So I can write this like so. Correct? At any x0. Everybody with me?
Yeah.
Okay. So that means I can write this guy like so. So let's say WK is my current estimate, right? Then I can write E as E of WK plus E prime of WK times W minus WK plus half E double prime of WK times W minus WK squared. And this is exact, right? That's what the Taylor's theorem says. Everybody with me so far? Just raise your hands if you get that. Okay, I have 50, so I'll take that for a yes. Now, suppose I got this function over here, right? So let me erase this stuff at the bottom, if I can pick this pen. So I have this function. Where will it be a minimum? How do I solve for the minimum? What would I do? How can I solve for the minimum? Yeah. I can just differentiate and set it to 0, right? Correct? What is the derivative with respect to x over here? Anyone want to help me? What's the derivative with respect to x? Someone help me, guys. The derivative, this has a derivative of 0 plus this one's derivative is simply f prime of x, x0, correct? And this one's derivative is going to be 2.5 cancel out plus f double prime of x0 times x minus x0, right? Yeah. And so if I try to solve for x is going to be what? This is going to be f prime. I can divide everything by x0. This is going to be x0 minus f prime of x0 divided by f double prime of x0.
So in
times-
this case, the third derivative is 0 of fx is 0.
Yeah, correct, right?
Okay.
So does this make sense?
Yeah.
Is this the correct answer, right? Yeah, okay. So that's what I'm going to say. You're saying that the minimum is WK minus the inverse of the second derivative times the derivative at WK. Now compare this formula with the gradient descent rule. What is the optimal step size to get to the minimum in one step? Compare this formula to this guy.
Second
What is-
derivative inverse.
The second derivative inverse is going to be the optimal step size, right? The inverse of the second derivative is going to be the optimal step size. If you take that step size, you're going to get here in one step. That clear to everybody?
Professor, I'm still confused about how did you get the 0?
So meaning here, I just took this function, I'm trying to minimize it. To minimize it, I computed the derivative and set it to equated it to 0. Right?
Yeah.
That gives me this answer, right? If you just work it out. And so, are you clear about that?
Yes.
Okay, so that's all I'm doing. Respond to me, guys. We'll end up being very slow. Then I will have to take an extra class, okay? So this is the situation we have, which tells me that if the step size is the inverse of the second derivative, I'm going to get to the solution in one step. I don't need a second step. And so what happens? Let's say I'm going to ask you this question, answer me. I have a quadratic objective function, M over here, okay? My optimal step size is E double prime of W0. Let me call this W0, okay? Suppose I take a step size which is inverse. Suppose my step size is exactly this much. then in how many steps will I get to the minimum?
1.
I'm going to get straight here. Suppose the step size is less than this much. What will happen?
I have to take multiple steps to it.
I'm going to keep doing something like this, right? Suppose the step size is greater than this much. What happens?
Divergence.
You overshoot the minimum.
It will overshoot, but will it get to the minimum?
Eventually,
It'll keep
it'll
bouncing
bounce
around.
back.
Do that and get to the minimum, right? Is there a value of step size where it will not get to the minimum?
Well, if it's twice as big, then it's probably going to jump off.
Twice, then it's going to go up and then it's going to begin going out, correct? That making sense to everybody, right? And so here is the situation you will have. If you have an optimal step size, you get here in one step. If it's less than the optimal, you're going to go down like so. If it's greater than the optimum, you're going to bounce around on either side, but you'll get here. Except if you have more than twice the optimal step size, in which case you're going to actually diverge. So for less than opt, it's a monotonic solution. Eta opt, it's monotonic. If it's between 2 eta opt and eta opt, it's an oscillating convergence. If it's greater than 2 eta opt, it's divergence, right?
And if it's exactly 2, it stays on the same place, same 2 places.
Exactly. It's going to keep bouncing around, right? So Neil will get to that. Shrikaran, there was a question.
Yeah, are you assuming that the step size changes as through number of iterations?
Does the double derivative change?
No, the step size.
The step size, I'm speaking of a fixed step size, gradient descent, yeah. Okay.
Professor, how did you get this value 2 times optimum learning rate? Is the threshold for?
Because if it's optimum, it comes here, right? So if it's 2 times optimum, it's going to do this and come right back here.
Okay.
Correct? Yeah.
Okay.
Professor, even if the step size is less than the optimal step size, I think maybe it might cannot converge if you set the threshold for the converge is too small.
It will take a long time, but it will converge. It will take a long time, but it will converge. So long as you're moving.
I see.
Right.
I see. Yeah.
Now you're asking about quadratic functions, non-quadratic functions. Any differentiable convex objective function, I can take a second order Taylor series approximation of this kind, right? So if this orange curve is my curve, my second order Taylor series approximation is going to be this quadratic bowl. And for that quadratic bowl, I can actually get to the optimum in a single step by taking a step size, which is the inverse of the second derivative at this point. This is actually the logic behind Newton's method. And if your step size is more than twice that much, it's going to diverge, okay? So this is for a scalar function. Now, what if I have a multivariate quadratic, which is a function of many variables, right? A multivariate quadratic, yeah, it is, right? So for a multivariate quadratic is going to have this form. W is now a vector. The quadratic is going to be half of W transpose AW plus W transpose B plus C. Still a quadratic, except in vectors and matrices. Now, for convenience sake, I'm going to assume that A is a diagonal matrix. This doesn't, none of this depends on A being a diagonal matrix. I'm just assuming this for convergence. It's like rotating my paper so that A becomes diagonal, okay? Then my objective function ends up being a sum of many independent quadratics, one along each dimension. Is this making sense to you guys? This one?
Yeah.
Professor, can you repeat?
So if A is this is a multivariate quadratic function, right? Because it's a multivariate quadratic function, it has the form half of W transpose AW plus, BW plus C. But if A is a diagonal matrix, then this product simply becomes W1 squared A11 plus W2 squared A12 and so on, correct?
Yeah.
So, and because of that, I can write this whole thing as a sum of many quadratics. And so the quadratic, the contour plot of a quadratic is always a bowl. So the contour plot of this multi-dimensional, multivariate quadratic is going to look something like this guy. It's going to be elliptical, aligned to the axis with different eccentricities along the different dimensions, because the eccentricity depends on the second derivative A. So is this picture making sense to you guys? This visualization? Yeah, okay.
Yes.
So now what happens? If I take a slice of this quadratic at any point, if I take a vertical slice of this quadratic at any point, because it's a sum of many different quadratics, I can think of if I change x, so if I think of this whole thing can be thought of in 2 dimensions as a quadratic of along x plus a quadratic along y, correct? So if I take the slices at different x's, along x, along y, it remains a quadratic. The only thing that changes is this extra bias term. So all of these quadratics are going to have the same shape. They will have, the only thing will be different is the different heights, right? What about the positions of their minima? Will they be different?
It should be at the same place.
Exactly. So the quadratic for the minimum along the x-axis is going to be the same for along the y-axis is going to be the same for every y. The minimum along the x-axis is going to be the same for, wait, the minimum along the y-axis is going to be the same for every x, and the minimum along the x-axis is going to be the same for every y, right? Same place, different value. You get that. And so now, these are all the quadratics along x, these are the quadratics along y. What is the optimal step size along x?
The inverse of the second derivative to x.
Which is going to be a11 inverse, right? What about this guy?
The same for y.
It's going to be a22 inverse, second derivative for y, correct? Inverse to the second derivative for y. Now, now here's what happens. When you're doing gradient descent, you're going to have something of this kind. You're always taking a step against the gradient, and the gradient, you know, is perpendicular to the equal value contour. This is not Abuzar, it's a bowl, it's not a Gaussian, right? Chinmay, this is the not WI. Basically, I said the entire quadratic is the sum of quadratics along every dimension. So this is a quadratic along x plus, if I think of it as a function of x, it's a quadratic along x plus terms that don't depend on x. If I think of it as a function of y, it's a quadratic along y plus terms that don't depend on y. That's all, right? The minimums, the positions are going to be the same, the values are going to be different, right? So now, what happens? If this gradient descent rule is going to use the same step size for every component, every dimension, right? What can be the problem with having the same step size for every dimension? Remember that, actually, let me show this with pictures, right? Without even showing you the picture, let me draw this and you guys can tell me. So you agree that if I have a function of this kind, the optimal step size can be different in the different directions, correct? You agree? So suppose my optimal, so in this function, along the y direction, along the x direction, the optimal step size is going to be smaller than this guy, right? Where it's steeper, the step sizes are smaller. So let's say along the x direction, the optimal step size is, say, 1. Along the y direction, the optimal step size is 2, okay? If I use a step size of 2, what will happen? Starting from some point.
It'll overshoot the x minimum.
I'm going to get to the optimum along y in one step, but along x, I'm going to begin bouncing, right? So that's basically what will happen over here. If I have something of this kind, here, if my step size is less than the optimal step size in the vertical direction, it can still be more than twice the optimal step size in the horizontal direction, and I'm going to end up having this kind of behavior, right? So here in this case, for example, my step size is 2.1 times, it's exactly twice the optimal step size in the horizontal direction. And you see what happens. It's converging along Y, but along X, it keeps bouncing. In this third case, the step size is less than the optimal step size for both directions, but it's still more than 1 times the optimal step size along X, although it is less than 1 times the optimal step size along Y. And so it's going to bounce around like so. But it's going to come to this point. Now here is something. In this case, the step size is exactly the optimal step size along X. But as a result, it becomes much lesser than the optimal step size along Y. And so along X, it gets to the optimum in 1 step, but then it takes a long time to converge to the solution along Y. And here, it's less than the optimal step size along both directions. So the convergence is going to be really slow, right? Is this making sense to you guys, this picture?
Yes.
Yes.
Any questions?
Professor, the first 2 images, can you explain again?
So in the first image, the step size I'm taking is less than the optimal step size along Y, but it's more than twice the optimal step size along X. So if you look at the convergence along Y, in the Y direction, it converges, but in the X direction, it diverges, right?
Yes.
Over here, it is less than the optimal step size along Y. It's exactly twice the optimal step size along X. So at twice the optimal step size, it keeps bouncing around, but never converges in the X direction, but it does converge in the Y direction.
Okay,
So
yeah.
UA, did that make sense to you?
Yes, yes.
So this is to UAN. Does that make sense to you? All right, I'll move on, right? So X and Y are the 2 variables, correct, yeah. So which option is appropriate, Aditya? Can you answer me?
Second to last.
It has to be, so what is the criterion you can make? Every dimension has a different optimal step size, right? So you want the step size to be, twice the optimal step size is still tolerable. I mean, slightly less than twice the optimal step size. So you want the step size to be smaller than twice the smallest optimal step size, correct? But then the eccentricities along the different dimensions can be wildly different. So when you try to make this smaller than the smallest, twice the smallest optimal step size, then along that dimension, you may converge properly, but in other dimensions, you can become so slow that the learning can become very slow. And even so, in directions where you lie between the optimal and twice the optimal step size, you can keep bouncing around. So now this is for quadratic functions, right? What does the inverse Hessian do, Burhan? Can you tell me?
The optimal step size.
What inverse Hessian does? Here's what it does, and all of you are giving me the correct answer at some point. What the inverse Hessian will do is it's going to, when you multiply the variable by the inverse Hessian, it's going to normalize the curvature along every direction, and now the equal contours, the equal value contours will become circular, and the optimal step size will become the same in every direction. That's why you need the inverse Hessian. What can be the problem with the inverse Hessian?
If the Hessian is 0, it can be infinite.
How many parameters does your network have?
N dimensions.
How many, and how in your network, how large is your network? You can have millions of parameters, correct? What is the size of the Hessian? Million squared. How are you going to invert it? Right? you cannot use inverse Hessians because it's computationally infeasible. So if you have non-convex functions, here is what happens. Then for non-convex function or non-quadratic functions, non-quadratic convex functions, I can still make a Taylor series approximation of vector functions. Everything that we said still holds. But the problem is that you can have different optimal step sizes along different dimensions, and the whole thing can become a problem. And convergence behaviors become increasingly unpredictable as the dimensions increase. For fastest convergence, ideally the learning rate must be close to both the largest step size and the smallest step size. So you want the largest optimal step size and the smallest optimal step size. So if you want it to converge in a nice, beautiful way, you want the ratio of the largest optimal step size and the smallest optimal step size. What do you want that ratio to be?
1.
You want it to be 1. You want the optimal step size to be the same in every direction, right? Abuzar, there's no guarantee that it will be invertible either. So, that's a different problem, right? So I have a bunch of slides which talk about how you can try to fix this problem by normalizing by the inverse Hessian. The math is there, but then you run into the issue that the Hessian can be too large and it can be uninvertible. And there's a lot of math, many techniques which try to approximate the inverse Hessian using various methods. But then, is divergence really a problem? Even assuming that I'm going to be taking a step size, which is, some step size, some fixed step size, is divergence really a problem? So here's what happens. Think about this. For complex models such as neural networks, the loss function is not convex, right? So having a step size which is larger than twice the optimal step size can actually help escape local optima, local minima, right? If you're here, for example, if you had a nice convergent step size, you'd end up over here, whereas where you want to be is here or preferably over here. So you want the step size to escape this, you want the step size to be greater than twice the optimal step size. On the other hand, if you're always greater than twice the optimal step size, what happens?
You never converge.
You never converge, right? And so what we want is to start with a large step size, large learning rate, greater than, twice the optimal step size, and then keep decreasing it with iterations. And the idea is that when you do that, initially you will bounce around, but eventually you'll end up in a large bowl where your step size is smaller than twice the optimal step size for the bowl, and then you will actually find the minimum of that bowl. So having
Professor,
a large...
but why do we assume that the first bowl that we are in is less good as the second bowl that we will reach?
So the point is, we are not necessarily assuming that. The implicit assumption is this, that a good minimum is going to be big, right? And so the scaling down, you're going to be something like this, right? If you happen to be in this bowl and you start off with a larger than, large initial step size, you may initially diverge, but because you keep shrinking it, you will eventually get to the minimum.
All right, I see.
Whereas if you start over here, you're going to definitely escape it. Right?
Yeah.
Make sense? So this is this is why you want to have a large initial step size and shrink it. And this is where we speak of all of these learning rate schedules, right? You start off with a large step size, and at each iteration, you keep decreasing the step size. There are all kinds of schedules that have been proposed. You decrease with the epochs, with the iterations. It's proportional, the step size is proportional to 1 over k plus 1, where k is the iteration number, or the quadratic decay, which is decreases as k plus 1 squared, or the exponential decay. You can come up with your own schedules. You've been working around this, right? So we chose our loss. Yeah.
Yeah, doesn't mean that it might not be the best solution, but it can be a better solution.
Exactly. Over here, see the step left one is not the best solution, but it's definitely better than where you began, right?
I see. Thank you.
Yeah, May wants to. All right. So, okay. So the story so far is that gradient descent can miss obvious answers, and this may be a good thing. Convergence issues abound. The loss surface has many saddle points, many local minima, and vanilla gradient descent may not converge or may converge too slowly. And the optimal learning rate for one component may be too high or too low for others, right? So this is what we've seen. Now I have another poll. Sort of running out of time, amazingly enough today yet again, but yeah. We have 25 minutes. This is an easy one, guys. No poll. That's the easiest one, Karan. You don't see the poll at all. But I'm sorry, this is just Zoom has these poll issues. I'll stop in 5 seconds. Again, I apologize for Zoom, guys. It's not my fault, but it's happening in my class. I'm sorry. Okay, let me stop this. It is. Only the first one is true. Step sizes that are greater than twice the inverse of the second derivative can cause gradient descent to diverge. But in some situations, this may not be a bad thing. We saw that, right? And gradient descent will converge with fixed learning rate if your function is quadratic, for example, right? You don't need decaying learning rates. Decaying learning rates are just a heuristic that allows you to start large and shrink and escape bad local minimum. So divergence causing learning rates we saw may not be a bad thing. Decaying learning rates provide good compromises between escaping poor local minima and convergence. But many of these issues arise because we force the same learning rate on all parameters. And many of you have pointed out that the sensible thing to be doing is to have a parameter-specific learning rate, right? The problem is now you'll have to keep track of many different parameters, many different learning rates. And even if you are keeping track of many different learning rates, it's not obvious what the optimal learning rate for any given parameter must be because you haven't seen the loss function along that dimension. And so let's take a step back. Problems arise because of requiring a fixed learning step size across all dimensions because all steps are tied to the gradient. I'm going to take a step back. I'm going to release this requirement. I'm going to come up with present some algorithms that use the derivative information for trends, but do not follow them absolutely. So the idea is we will not have the same learning rate for every dimension, but in that case, we are left with the problem of knowing what the optimal learning rate must be for each dimension. Even that is not known. So that problem too must be solved in the process. And if you've used Adam, for instance, you will see that you actually end up with a different learning rate along each dimension. And the mechanisms we use over there actually sort of try to find the optimal learning rate for every dimension. But before we even go there, let's look at a couple of other solutions. The first one is RProp, called resilient propagation. It's a simple algorithm to be followed independently for each component. So if you have a many multi-dimensional function, like in your network, every network parameter is a dimension, then you follow RProp independently on each component. So the optimization along one component does not consider the other components. So at each time, what we do, let me show this with pictures, right? Let's say you start off at this point, right? Your initial guess. And you're the very first time you have some step size, you're going to check the derivative, but the only thing you're going to use the derivative for is to determine if you should be increasing, if your estimate for the parameter should be moving right or if it should be moving left. If the sign of the derivative is negative, you should be moving right. If the sign of the derivative is positive, you should be moving left. That's the only information you're using from the derivative. So here, for example, the derivative sign is negative. So you initially will take a step forward and come, maybe this is your initial step. You come here and that comes over here, right? Then you check the derivative over here. You check the derivative again over here. If the sign of the derivative in both cases is the same, then are you going in the correct direction or have you overshot?
Same direction.
Correct direction.
The same direction, right? So in that case, what would your logic be? Should you increase your step size or decrease it? Should you become more conservative or less conservative?
A bigger size.
So all you will do is say, okay, this derivative and this derivative had the same sign. I'm going to multiply my step size by some alpha. Boom, I go here. I check my derivative sign again. And I find that between this position and this position, the sign of the derivative has not changed. What will I do to my step size? Increase it again, right? Because I'm going in the correct direction. So I increase it, and now I take this step. And now I end up over here. And now I find that the sign of the derivative has become positive. The sign of the derivative has changed. What does that tell me?
Time to
You overshot.
Time to,
That I
lower the
overshot. If I overshot, then what is the correct thing to do?
decrease.
decrease the learning rate.
What I can do is go back over here and scale down my step size, right?
Yes.
Basically, I go right back and then I go forward, and now I decrease my step size with some beta and repeat the process. Eventually, you're going to find the minimum, right? Does that make sense?
Question, Professor, any reason why we don't simply reverse with a smaller step size instead of going back to where we were before?
That's like starting back, because now when you reverse the step size, right? You still have to shrink the step size. And it's like starting RProp all over again. You've lost information about the past, that's all. So you could do that. Either one is fine, right? So
another question,
you could do that. They're different. The point is what you do when the step size changes, the sign changes, is a heuristic that there are different heuristics. You can try any of these, whichever makes sense, right? The point is, this is a performed independently. I have a pseudocode over here. I want to explain it. It's performed independently along each dimension. The only thing that you have extra is that you always have a ceiling and a floor on the step size. So you don't let the step size get too large. You don't let it get too small. If it's too large, you can, you may go so far that you may skip multiple local minima. If it's too small, you will never converge. And then besides that, you can just use this to update your network. So the key point here is that this is not actually using the value of the derivative. Is this using the value of the derivative anywhere? I just gave you the answer, guys.
No, it's not.
No.
What is it using from the derivative?
Sign.
The sign.
Just the sign, right? And based only on the sign, it decides whether it's going in the correct direction or whether it's overshot and corrects. That's it. It turns out
Can
this
I
is a
ask
very
a question, Professor?
Yeah.
So when we were increasing the learning rate, well, not the learning rate, but the step size, I mean,
the same as the learning.
We first multiplied by alpha.
Yeah.
Then when we're increasing for the second time, we multiplied by alpha squared.
No, you multiply the previous step size by alpha. So the net is alpha squared.
Okay. And then, so for the third time or fourth time, up to the nth time, we continue multiplying by the previous step size by alpha.
Times alpha. That's it. Right? And so, so beta is going to be less than 1. Alpha is going to be greater than 1. That's correct, right? So it's a remarkably simple first order algorithm. You don't compute second derivatives. And it's much more efficient than gradient descent. And it turns out it can actually be pretty competitive against many of the more advanced second order methods that are out there, and makes only minimal assumptions about the loss function. Definitely does not assume convexity. So it's a really nice method, which leads me to pole 3. Here, I even get all the way to pole 4 today. So we are not speaking of local minima over here, Shreya, but the point is that if your step size becomes, if your step size keeps increasing, then you can run some simulations. You will see that you will generally escape local minima because of the nature of the loss function. But there's no explicit mechanism for escaping local minimum. Okay, 5 seconds, guys. All right. So in the classical definition of RProp, the first one is true. You go back and then take a smaller step size. But you can, in fact, as someone pointed out, you can actually reverse direction and begin taking steps in the opposite direction. The first one is going to be more efficient than the second one in most situations. So, and typically because when you overshot and shoot a minimum, your step size is generally so large that you may end up at a greater loss value than where you began from. So why not? The second is simply this. The logic is this, that when this happens, your step size is generally very large. So if you have an objective function of this kind, if you take a large step size, then you're going to end up at a greater loss than where you began from. That's all. So it's just a heuristic, right? Alpha is greater than 1. Alpha is increasing the step size. Beta is less than 1. It's decreasing the step size, right? There's another method called QuickProp, which is like Newton's method updates, but does this without explicitly computing second derivatives. And this was proposed by our own Scott Fahlman. It's, but that's a heuristic. I haven't seen any typical values for it. But anyway, the QuickProp is proposed by Scott Fahlman over in SCS and is one of the more cited approaches. This goes back 30 years and is completely competitive with modern methods. And this is like Newton's method, except Newton's method requires the computation of a Hessian and an inversion of a Hessian, which you know is very hard. So this uses an Euler approximation to compute the second derivative along the path that you take for optimization. You should look it up. It's on the slides, right? So the story so far, second order methods, vanilla gradient descent, maybe too slow or unstable due to the differences between the dimensions. We saw that, right? And second order methods, which normalize the variation across dimensions by the Hessian, can make things better, but they are complex, computationally infeasible. Adaptive or decaying learning rates can help you escape local minima and improve convergence. You can also get better convergence by methods that decouple the dimensions, but then you're left with the problem of figuring out what the optimal step size is along each dimension. So, any questions so far?
I have one more. So,
go ahead.
Okay, so when we decide that, okay, we have overstepped, our step size is now too large, we have to revert back to the last place where we were when the when the direction of the gradient was still the same as what we were expecting. So we then reduce the step size by beta. Is there a relationship between the size of alpha and beta?
Those are heuristically chosen. The only thing we know is beta has to be less than 1.
Okay.
right? And so you, and anyway, so second order, you hang, this is this one. We said that you can, I won't actually go there, too many slides. We said that you can normalize the directions by multiplying by the inverse of the Hessian. The Hessian is a second order derivative. So anything that uses second order derivatives is what we are calling a second order method. And again, those remember what I said about Hessians. I have one more topic to go through, but if I have a loss function which looks like this, and then I take my data and just put it through the inverse of the Hessian, then what will happen is that this loss function is going to become circular. The eccentricity along every direction is going to become the same. And now the step size in every dimension is going to be the same. Does that answer your question? Okay. So with dimension independent learning rates, the solutions will converge smoothly with dimensions independent learning rates. If you have the same learning rate in every dimension, the solution will converge smoothly in some directions, but may oscillate or diverge in others. We have this issue, right? So the real issue is this oscillation, correct? You want smooth convergence. You don't want oscillatory behavior, let alone divergent behavior. Even oscillatory behavior is not a very good thing. Definitely don't want this behavior. And even this is not great. So here's what we will do. Let's keep track of oscillations and let's emphasize steps in directions that converge smoothly and shrink steps in directions that bounce around. So here, for example, I would like to emphasize steps in the vertical direction and shrink the step size in the horizontal direction. That will give me smoother convergence, right? So that leads us to two kinds of methods. First is the momentum methods, which I'll briefly touch on today. And the second is Adam and such like, which we will see later, next class. So here is what the momentum method does. It maintains a running average of all past steps. Now, in the directions in which the convergence is smooth, the average will have a large value. In directions in which the estimate swings around, the positive swings and the negative swings will cancel out when you take an average. Then you're going to update with a running average rather than the current gradient. So is this making sense, guys? The logic here?
Yes.
Any questions? No, okay. So this is the basic idea of a momentum method, right? How do we do this? There are a couple of different ways of doing it. So what we do is that you maintain a running average. What we want to do is to keep and maintain an average of the gradient over the past several steps. And the gradient includes the partial derivatives along every dimension. So when you maintain an average along dimensions where they always had the same sign, the average is going to be nice and smooth and it's going to be large, right? So for example, if I looked at the gradient over the past several steps, and the gradients was 1, -1, 1, 1, 1, -0.5, and say 1.5. If I take an average of these will give me a 1. But here the positives and negatives will cancel out and give me a 0, right? And what I can make out from here is that in the horizontal direction, it's going smoothly. In the vertical direction, it's bouncing around, right? From the gradients. This making sense, guys? I'm trying to scribble on a vertical screen, so my handwriting is horrible, right? But so that is the basic idea that we are going to use. And specifically, the mechanism that we are going to use is a running average. So you're going to say that the current step size is going to be some beta times the past step size plus whatever step size is suggested by the current gradient. So you're averaging the current gradient with the steps taken so far. And this step is what you're going to be adding to the W parameter to get the updated W. So is this equation making sense? Right. So this gets longer in directions where the gradient retains the same sign. It becomes shorter where the sign keeps flipping, right? Basically, there are different ways of doing it, but this is maintaining a running average of the gradients. And when you maintain a running average of the gradient, you don't just use the latest gradient. You say you take some beta times the steps taken so far, the running average so far, plus the current gradient. That's going to smooth them out, right? And that's what you will use for updates. So again, I have the pseudocode over here. What you will do now is you compute the derivative and the gradient. This is a standard gradient descent, and you just update by taking a step against the gradient. But for momentum, here's what you will do. You compute the gradient, but then from the gradient, you first compute the running average of the step, which is going to be beta times the previous step minus a step against the current gradient. And this running average is what you're going to be factoring into the estimate, right? And so when beta is 0, this is going to be a not standard gradient descent. Yes. Now, here's the thing. If you look at momentum, what's happening? Let's say you took a step so far, that is over here, correct? The previous step. Then over here, at this point, you found this to be the gradient. Then the actual step size is going to be some beta times the previous step. I mean, this is the step against the gradient. The gradient is pointing upwards. This is the gradient step. So the actual step is going to be some beta times this red arrow plus the blue arrow. So you will, to this blue arrow, you'll be actually adding some beta times this red arrow. And that is going to be your final estimate. So this is what momentum does. Is this picture making sense, guys?
Could you repeat again, Professor?
So let's say this was your previous step size, right? This was the previous step that you took. This was the estimate. Then in the previous estimate, you came from here to here. So this was the last step that you took. Okay. At this point, the gradient suggests that you should go this way. So the actual step is going to be this plus some beta times this red guy, which will bring you here. And that is going to be your next update. That is the momentum update. Okay.
So the red vector is a bit smaller than the previous one because it is multiplied by beta.
Exactly, right? This is momentum. But now what happens over here? You're computing the gradient and then adding the previous step size, right? What if I change the order? So what do I mean by changing the order? So here, you first computed this guy, gradient step, and then added in beta times the previous step to give you the final update. Let me change the order. Here, first I will take beta times the previous step further, then compute the gradient over here, which is going to be orthogonal to the equal value contour, and that is going to be my final step. So you see the difference between the two steps? T transpose. Do you see the difference between these two guys? Yes, no, guys. The results are not,
yes.
Right? The results are not the same. And so this is called Nesterov's method, and it's guaranteed to be better than the regular momentum, right? Because it sort of makes a predictive change. It says, what will my gradient be in the next step? And so Nesterov's method, I have the math, but rather than going through the math, the pictures are obvious. From the current estimate, first you don't compute the gradient over here. You add the beta times the previous step and then compute the gradient over here and then take the gradient step. That is going to be our final update, right? So this black line is going to be our next update. And so if you compare Nesterov's with regular momentum, here's what happens in this example. This is from Hinton. If this was your previous step, with momentum, you would first take a gradient step up here and then add beta times the previous step, and you'd end up where this blue line ends up. With Nesterov's method, you would continue along the black line to this point and then take a gradient step and you'd end up over here. which of these two is getting you to the optimum faster? The second method, right? The second method. So Nesterov's momentum is actually faster generally than plain momentum. It's a little more complex to implement, but it's doable, right? Here in this case, it gets it in 2 steps. So again, I have pseudocode for Nesterov's momentum, and you can look it up. So that's kind of come to the end of today's topic. It's a semi-complete lecture. We will continue in the next class. Sichi, that's actually, there's a lot of math behind it. You should look at Nesterov's paper. It's beautiful math. It's understandable for most people. But actually, I'm lying. The first time I read Nesterov's paper, I remember the paper said the first line had this equation which said obviously and gave me an equation. It wasn't obvious to me. So I took it to my student who had won mathematics Olympiads, silver medalist. And I gave it to him and saying, this is not obvious to me. Can you make it obvious? It took him 24 hours to figure out why it was obvious. This is, and so Karan, you and I are in the same boat. I'm not most people. Most of us are not most people. But anyway, this is, we will return to this, but it's provable, yes. Last poll and the class is done. Thank you, guys.
Professor, I had a doubt.
Yeah.
In momentum, when you showed that we are adding the vectors when like the previous step was multiplied by beta. So even if we are not using momentum, so even in that case, beta will just be equal to 1, right? So even in normal gradient descent, I'll be adding the vector.
Beta is going to be 0, right? You're not adding the previous step to the current step. Okay, let me stop this.
Okay. Right. Okay, understood. Right.
Yeah. So this one is, if you have a flat constant slope, then momentum is simply not going to change anything because the running average is going to be the same as the current slope, correct? Momentum only changes things if you have oscillation. So anyways, so here's the story so far. Adding momentum methods which emphasize directions of steady improvement are demonstrably superior to other methods. We're going to look at stochastic gradient descent, and we're going to revisit trend algorithms next week. That's okay, guys. I'm going to try to be in class. We were going to be in class today to try out our microphone and such like, but we were all warned not to ask students or ask anybody to ask even my TAs to venture out in this weather. So we will be testing out tomorrow.
Hi, Professor, can we say using the momentum instead of directly using the gradient descent, because the gradient descent is maybe too aggressive, so we add a beta terms like the step
the point is this. So the beauty of this is that momentum is probably better than gradient descent on convex functions and such like, because if you have a completely flat surface, the two become the same, right? And so on a flat surface, momentum collapses to regular gradient descent. And then on other surfaces, it basically smooths out oscillations. So it's actually going to be better.
Cool. Okay.